Good morning, students. In last class, we discussed about the PN junction diode biasing types, and then we discussed about the forward biasing and reverse bias. Then after we discussed about the junction breakdown techniques. Again, in that we discussed about the avalanche breakdown and Zener breakdown. Along with we discussed the VI characteristics of PN junction diode and resistance offered by the diodes. Today we will discuss about the current components present in the PN junction and diode current equation derivation. First, we will discuss about the P and diode currents. It is nothing but what are the different types of current components present in PN junction. So basically, the charge gas present in the PN junction are two types. One is hole, another one is electron. So the total current in the PN junction diode nothing but the sum of current due to holes and electrons. Again, we already know there are two different mechanisms to get the current. One is drift mechanism, another one is diffusion mechanism. So holes drift current, holes diffusion current, and electron drift current, electron diffusion current. So here we can observe these four currents in PN junction diode. So we'll discuss in depth. Holes travel through P region because of repulsion from positive terminal of external battery. Hence, hole current through P region is drift. Yes. So in forward bias, we are connecting the positive terminal of the battery to the P region and negative terminal of the battery to the N region. So when we are connecting the positive terminal of the battery to the P region, due to the repulsion from the positive terminal of the battery, the holes in the P region are repulsion towards to the junction. So holes are traveling through the P region because of repulsion from positive terminal of the external battery. Hence, the hole current through P region is drift. So when charge gases are moving due to the reason of external battery or external electric field, then that mechanism is called drift mechanism. So the holes in the P region are moving due to the repulsion of positive terminal of the external battery. So the current through the P region due to the drift mechanism. So this current is called hole drift current. Yes. So now the holes are moving towards to the junction. So that means the more number of holes are accumulated at junction. So we are considering that direction is x. So the junction point is, we are considering x equals to 0. So when holes reach the junction, they enter N region mainly because of gradient, concentration gradient. So in P region at x equal to 0 or junction point, due to the drift mechanism, more number of holes are accumulated at junction x equals to 0. As in the N region, minority of the charge carriers are holes. So when you are observing at x equals to 0 or at junction, we can observe in at P region, large number of holes are accumulated. In N region, less number of holes are present because it is N region. So we are having minority of the charge carriers. So now we can observe the concentration gradient, hole concentration gradient. That means one side we are having the more number of charge carriers and another side we are having the less number of charge carriers. Yes. So one side we are having the more number of holes, in another side we are having the very small number of holes. So now we can observe the concentration gradient. When concentration gradient is present, then diffusion mechanism will appear. Yes. So when concentration gradient is present, diffusion process present in this case. So due to the diffusion process, that holes are moving into the n region. Yes, you may ask, sir, we are already applying the electric field. Yes, so that electric field affects on holes. That means that due to the electric field, that the holes are traveling from one end of p region to the at junction point. That is called drift mechanism or drift current. At junction, holes are accumulated. So on that holes, the electric field is applied as well as we can observe the concentration gradient. So compared to the electric field or compared to the external battery effect, the holes are moving into the n region because of concentration gradient. So we are considering mainly concentration gradient. Yes, at x equals 0 at junction, the holes are moving into the n region because of concentration gradient due to the diffusion process. Yes, hence this current is called, or hence whole current through the n region is called diffusion current. Yes, whole current is maximum at the far end of the p side, and whole current is gradually reduces because hole keeps recombining with electrons coming from n side. Yes, whole current becomes almost zero at far end of n side. So whole current is maximum at far end of p side. When it is entering into the n region, then current due to the holes is almost to zero. Why? Because when holes are entering through the junction, then the majority of the charges in the n region are recombined with the holes. So concentration of holes are becomes reduces or decreases. When concentration of holes reduces in the n region, so whole current in n region becomes zero. So the maximum whole current can appear at far end of p side, and minimum whole current appear at far end of n side. Clear? This is whole current. Now we are discussing about the electron current. Now free electrons are travel through the n region because of repulsion from negative terminal of external battery. Therefore, electron current through n region is a drift current. Similarly, whole current, when you are connecting the forward bias, the negative terminal of the battery is connected to the n region. Yes. So, due to the repulsion from the negative terminal of the battery or external battery, the electrons in the n region are moving towards the junction. Yes, when electrons are moving in the n region because of external battery or external electric field. So this mechanism is called drift mechanism. Yes, therefore current or electron current through n region is a drift current, and this drift current we are considering from one end of or far end of n region to up to x equals to 0 only, or at junction point. Yes, electron reaches the junction, enter p region mainly due to concentration gradient. Similar to holes, now electrons are reached towards to the are reached at the junction or x equals to 0 point because of drift current. After reaching to the junction at n region, we can observe the concentration of electrons is more compared to the p region, because in p region minority charge carriers are electrons. So in p region electrons are minority charge carriers, in n region electrons are majority charge carriers. So due to the concentration gradient, here also we can observe the concentration gradient of electrons. So when concentration gradient is present, we can get the current due to the diffusion process, only. Yes, when electrons reach the junction, enter p region mainly due to the concentration gradient. Therefore, electron current through p region is diffusion current. Clear? Next, free electron current is maximum at the far end of the n side, and it is gradually becomes zero at far end of the p region, because entered electrons are recombined with the majority of the charges of p region. Yes. So when entered electrons reaches to the p region, the far end of the p region, the electron current becomes zero. Clear? Here you can observe the diagram. So here I mentioned at x equals to 0. That means it is indicating the at junction point. Yes. So whole current, it is represented with IPP of x. So this IPP of x is whole current and it is drift current. Yes. So IPP of x is nothing but I is nothing but current due to the P. First P indicates the type of charge carrier and second P indicates the type of region or type of material. Yes. So IPP of x is nothing but whole drift current in P region. It is varying with x distance. Yes. That holes are entering into the n region at x equals 0. It is represented as IPN of x. It is exponentially decaying or decreasing. Yes, here I am keeping cursor. Are entering into the n region, holes are entering into the n region because of diffusion. So IPN of x, current due to the holes in n region, this is called hole diffusion current in n region. Yes. So now I am indicating electron current. So electron current, I am keeping cursor. Electrons are at x equals to 0. It is indicated as I ln of x. This current is due to the drift mechanism. So I ln of x is nothing but current due to the electrons in n region is called drift current. Yes. Now at x equals 0, it is gradually decreasing or exponentially decreasing in the p region. It is represented with INP of x. It is electron diffusion current in p region. Electron diffusion current in p region. So here we can observe total currents are 4. Electron drift, hole drift, electron diffusion, hole diffusion. So here I mentioned components IPP of x is nothing but current due to holes in the p region. It is nothing but hole drift current in p region. Next, IPN of x, current due to holes in n region because of diffusion. So it is hole diffusion current in n region. Next, iron of x, this is current due to electrons in n region because of drift mechanism. So this current is free electron drift current in n region. Next, INP of X, this is current due to electrons in p region. Yes, because of diffusion mechanism. So this is called free electron diffusion current in p region. So now we know the current components in the diode. Current is nothing but sum of all current and free electron current. It remains constant at any point x. The diode is nothing but sum of whole current and free electron current at any point. Nothing but it is x. Total current in P region. Total current in P region is the sum of whole drift current and electron diffusion current. So in this diagram in P region you can observe previous IPP of x plus INP of x. IPP of x is nothing but whole current in P region. INP of x is nothing but electron current in P region. So in P, whole drift current and electron diffusion current. So total current in P region is nothing but sum of whole drift and electron diffusion current. Similarly, total current in N region, sum of electron drift current and whole diffusion current. So now we mention current in P region, current in N region, current at any point in the diode. At junction x equals 0, at x equal to 0, total current is sum of whole diffusion current, electron diffusion current. So at x equals 0, we are considering current due to the diffusion process. Yes. So at x equals to 0 or at the junction point, total current is the sum of whole diffusion and electron diffusion. Hence, junction in forward bias is a diffusion current. Clear? When junction is in forward bias, we can observe the current at x equals to 0 or junction point only diffusion current. We will discuss about the diode equation or diode current equation. It gives the relationship between the current passing through a diode and voltage across the diode. Yes, this diode equation gives the relationship between the current passing through a diode and voltage across the diode. Yes, so consider a diode in forward bias at the junction. At the junction means at x equals to 0, center of the P region and N region. Total current is sum of whole and free electron current. So now we are deriving the diode equation. It is giving the relationship between the current through the diode and the voltage across the diode. So current through the diode is nothing but we are considering a point at x equals 0. So when we know the current at x equals 0 is nothing but current flowing in the diode. Yes, we are assuming the diode is in forward bias and at x equals 0. We are calculating the current at x equals to 0. Yes, so at x equals 0 we know. So we can observe only diffusion current, that is whole diffusion and electron diffusion. So when we are summing that whole diffusion and electron diffusion currents, we can get the total current at x equals to 0. So that is represented as I equals to I Pn of 0 plus I Np of 0. It is equation number 1. And I Pn of 0. So actually in previous we already it is x. So instead of x we mention it is equals to 0. Why? Because the center point or at junction point we are considering x equals to 0. So we replace that x with 0. So it is I Pn of 0 plus Inp of 0. So we know I Pn of 0 is nothing but I is nothing but current, P is nothing but due to the charge carrier, and N is nothing but type of region. As I Pn of 0 is nothing but the current due to the holes in N region at x equals to 0. As INP is nothing but the current due to the electrons in P region. These two are diffusion currents. So we name this equation as 1. Hole traveling from P to N and electrons traveling from N to P are called injected carriers. So holes are traveling from P to N and electrons traveling from N to P. These are called injected carriers. They are also called as excess carriers. Yes. The net hole concentration in N region will be sum of injected hole concentration and thermally generated hole concentration. So, due to the concentration gradient at x equals 0, holes are entering into the N region. Yes, that are injected hole concentration. That are injected from the P region to N region. So, that hole concentration is called injected hole concentration. And here we mentioned thermally generated hole concentration. Yes, so these holes are injected carriers, and some of the holes will generated due to the thermal excitation. That concentration we mentioned as thermally generated hole concentration in N region. So total number of holes or total number of hole concentration is equals to what we can write? Injected carriers from P region and thermally generated hole concentration in N region. Yes, clear? Total number of holes or total number of hole concentration in N region can be written as injected carriers from the P region and thermally generated hole concentration in N region. So due to the thermal excitation, some of the holes will be generated in the or inside the N region. Yes, total holes in the N region can be written as injected hole concentration from P region and thermally generated hole concentration in N region. Yes. So now here we can observe the diagram. At x equals to 0, Pn of x at junction, the total charge carriers accumulated, total hole concentration accumulated are Pn of x, which are ready to entering into the N region. Yes, and here I mentioned some gap. Exponential decaying graph. It is not directly connected to the x-axis, and here I written the here I drawn the straight line. So from x-axis to the straight line gap is nothing but Pn naught. Pn naught. It is thermally generated hole concentration. Yes, thermally generated hole concentration. This is written as Pn naught. It is equals to Ns square by N. We know it is minority charge carriers. So minority charge carriers is always represented with the from law of mass action Ns square by majority charge carriers Nd in N region. Yes. So Pn of x are holes accumulated at x equals 0 which are ready to entering into the N region. What is the concentration of injected hole concentration at x equals 0? So Pn of 0 into e power minus x by Lp, from that graph only we can write it is exponentially decaying. So exponential decays can be written as e power minus s. So it is minus x by, we have written x by Lp. Yes, here Lp is the diffusion length of hole. Lp sub L suffix p. Lp is the diffusion length of holes. It's nothing but the distance after which the injected or excess holes concentration in the N region. That means Lp is diffusion length of holes after injected into the N region, how much distance it is traveled, how much length it is traveled. Clear? Before recombination. So once holes are entered into the N region, then that holes will travel some distance. After that, what happens? That hole will be recombined with the electrons in the N region. So before recombination and after injection. How much distance, how much length it travels in the n region is called diffusion length LP. Clear? This injected hole density decreases exponentially with recombination. So we have written it is Pn of 0 into e power minus x by LP. Here you need to observe this Pn of 0 into e power minus x by LP. This P, here I will keep the this two P's. One is capital P, another one is small p. So don't confuse in this diagram. This capital P n of 0 into e power minus x by LP is the injected hole concentration. Yes, injected hole concentration. Along with we are having the thermally generated hole concentration that is represented with the small p suffix n naught. Yes, it is small p suffix n naught. Clear? So capital P n suffix capital P suffix n of 0 is nothing but the carriers at x equals 0 ready to inject into the P region. Clear? The carriers ready to inject into the n region at x equals 0. Clear? So the total or hole concentration in n region will be sum of injected hole concentration and thermally generated hole concentration. So the injected hole concentration is represented, it is exponentially decaying, so it is capital P n of 0 into e power minus x by LP. Yes, and thermally generated hole concentration, it is small p n naught. Small p n naught. Yes, so total hole concentration in n region, total hole concentration in n region is Pn of x at any point. Yes, so we mentioned equation injected hole concentration, it is depends on x and LP. Why? Because injected injected hole density decreases exponentially with x with the recombination. Clear? I have written total hole concentration or net hole concentration in n region Pn of x at any point. Pn of x equals to thermally generated hole concentration plus injected hole concentration. I mentioned thermally generated hole and injected hole. So here we are having the two types of holes. So in anywhere hole is represented with the P, but here I am representing with small p and capital P in alphabets. The small p indicates the thermally generated hole concentration and the capital P indicates the injected hole concentration. Clear? So you may not find the difference between the two, small p and capital P, in this PPT. So here I am highlighting with the yellow color. As injected hole concentration capital P is highlighted with the yellow color, and thermally generated hole concentration P, small p, I am not highlighting, it is representing with normal P only. Yes, total hole concentration in our net hole concentration in n region Pn of x equals to small pn naught, it is thermally generated hole concentration, plus capital Pn of 0 into e power minus x by Lp. Yes, so injected hole density decreases exponentially with distance x with recombination. Lp is called diffusion length of holes. Diffusion length of holes or excess hole concentration. Injected carriers also called as excess carriers. So here it is injected holes or excess holes. Concentration becomes 1 by E at x equals to Lp. If I am taking x equals to Lp, that injected hole concentration density becomes Pn of 0 e power of minus x minus LP by LP. Instead of x we are writing LP. That LP cancel. So e power minus 1, it is nothing but Pn of 0 by E. Yes. So here I calculate the current at x equals 0, at x equals to 0. Yes. So we are considering, or we are putting x equals 0 in equation number 2. Yes. So when we are putting x equals 0 in equation number 2, then what happens? Pn of 0. Yes. Net hole concentration at x equals 0 at junction point is equals to Pn naught, it is nothing but thermally generated, plus Pn of 0. Yes. From that I am writing Pn of 0 is nothing but injected holes at x equals to 0. That are Pn of 0 equals to Pn of 0 minus Pn naught. Yes. So this is equation number 3. Yes. This Pn of 0 is injected hole concentration at x equals to 0. This is capital P. Capital Pn of 0 is injected hole concentration at x equals to. When net barrier potential is Vb, then we can write Vb equals to. So here we can observe the net barrier potential, that Vb equals to what we can write when it is not, when net barrier potential is not equals to 0. Yes, it is nothing but Vb equals to some V0 minus B. So then we can write Vb equals to Vt into Ln Pp by Pn. Yes, majority holes, majority means holes in P region by holes in N region. Yes, for similarly Vb for electrons, then we can write Vb equals to Vt into Ln, what we can write Nn by Np. So this barrier potential we are considering whole current. In this case we can write Vb equals to Vt into Ln Pp by Pn. Otherwise you can write for electrons Vb equals to Vt Ln Nn by Np. Anyone, we are considering the whole current, whole diffusion current at x equals 0. Yes. So from that we can write Vb by Vt equals to Ln Pp by Pn. From that we can write Pp holes in P region equals to Pn into e power Vb by Vt. This is equation number 4. Yes. Now we are assuming my diode is in open circuit condition. That means we are not connecting any battery. Yes, it is in open circuit condition. It is in ideal. We are not connecting any battery sources to the my diode. Now, what is the barrier potential? Vb equals to V dot. Whatever the built-in potential is nothing but barrier potential only. Why? Because here we are not connecting any external battery. Then the net barrier potential equals to net built-in potential only. What is the built-in potential? By default, that becomes the barrier potential. So Vb equals to V naught and Pp equals to Pp naught. Pp equals to Pp naught. That means the holes in P region equals to Pp naught. That means holes in P region at x equals 0. Whatever the holes present at x equals 0, that becomes the total number of holes in the P region. Yes. Similarly, Pn equals to. Yes. Holes in N region equals to what we can write? Holes in N region at x equals to 0. Pn naught. Yes, that are thermally generated. Clear? So Pp naught equals to, we are substituting these values in the equation number 4, then it is equals to Pp naught equals to Pn naught into e power V naught by Vt. This is equation number 5. Now I am considering case 2. In this case, I am applying the forward bias. Then what happens? The barrier potential becomes reduces. It is nothing but V naught minus V. Whatever the we applied potential is subtracted from the built-in potential. Vb equals to V naught minus V. So again Pp equals to Pp naught. But coming to Pn, holes in N region becomes injected carriers. Pn of 0 plus thermally generated. Yes. So in forward bias, total number of holes in N region equals to whatever we written first expression, or equation 1 or equation 2. Yeah, first expression, it is Pn of x equals to Pn naught plus Pn of 0 into e power minus x by Lp. So it is equals to, we are writing at x equals 0, so it becomes Pn of 0 equals to Pn naught plus Pn of 0. So from that we can write Pp naught equals to Pn of 0 into e power v naught minus v by bt. So when you are applying the forward bias, depletion region width is assumed to be 0, assumed to be 0. Then we can write Pn naught into e power v naught by vt equals to Pn of 0 into e power v naught by vt into e power minus v by vt. So from the above equation we have written like this. Yes. So from that we can write Pn naught equals to Pn of 0 into e power minus v by bt. Yes. From that we can write Pn of 0 equals to Pn naught into e power v by bt. This is equation number 6, and this equation is called law of the junction. This equation is called law of the junction. This law of the junction implies that the whole concentration in n region in forward biasing is always greater than the thermally generated hole concentration. Yes, this law of junction is indicates that hole concentration in n region in forward biasing is always greater than the thermally generated hole concentration. So when you are applying the forward biasing, concentration in n region is always greater than the thermally generated hole concentration. So what we can write? That means Pn of 0 is always greater than the Pn naught. This Pn naught is nothing but, we already know, it is thermally generated holes in the n region. Substitute this equation 6 in equation number 3. From that we can write Pn of 0 equals to Pn naught into e power minus v by vt minus Pn naught. From that we can write Pn of 0 equals to Pn naught into e power v by vt minus 1. This equation is 7th equation. Clear? Let A be the area of the junction. So now the electrons are crossing the junction, yes, and holes are also crossing the junction. So now we are calculating the hole diffusion current. So for that we should know the area of the junction. So let we assume the area of the junction equals to A, hole diffusion current through n region at any point or at any distance x is IPN of x equals to A into JP diffusion. We can write the current density of holes due to the diffusion created as what we can write current due to the holes by area. Yes, J equals to I by J. So from that we can write I equals to A into J. So IPN of x is nothing but current due to the holes in n region at any distance x equals to what we can write A into area of the junction into current density of holes due to the diffusion process. So IPN of x equals to A into, we know the JP diffusion is nothing but current density due to the diffusion process equals to what we can write E into diffusion flux density. Yes, in diffusion and drift mechanism we know the phi P equals to minus E into minus dP into concentration gradient. So from that we can write the JP diffusion is replaced with minus E dP dP n of x by dx. This is concentration gradient. So in this Pn of x is replaced, we already know, yes, this Pn of x is replaced with Pn naught plus Pn of 0 into e power minus x by Lp. So we know this is equation number 2. From that equation we replace that Pn of x. Yes. So from that we have written minus AE dP into Pn of 0 into e power minus x by Lp, and derivative of e power minus x by lp equals to e power minus x by lp, and here it is minus x by lp is derivation equals to minus 1 by lp. Yes, lp is, we know, it is diffusion length, the amount of distance traveled the hole in the n region after injection before recombination. Yes, from this we can write ipn of x equals to ae dp by lp into pn of 0 into e power minus x by lp. Clear? As from that, so we are finding the diffusion hole current at x equals 0. So put x equals 0, from that we can, by substituting put x equals 0, ipn of 0 equals to ae dp by lp into pn of 0. Substitute equation 7 in above equation, that becomes ipn of 0 equals to ae dp by lp into pn of 0 into e power v by vt minus 1. This is equation 8. This current is whole diffusion current at x equals to 0 or at junction point. As ipn of 0 is indicating the current due to the holes in n region at x equals to 0 or at junction. Yes, so this current is whole diffusion current at x equals 0. Similarly, we need to know electron diffusion current. Yes or no? Yes. So similarly, we are writing the electron diffusion current. It is nothing but INP of 0 obtained by interchanging the N and P in the above equation, or equation number 8. So N is replaced with the P and P is replaced with the N. Now it becomes INP of 0. INP of 0 is nothing but current due to the electrons in P region at x equals 0. So that will be written as AE dN by LP. So dP is the diffusion constant of holes, dN is the diffusion constant of electrons. Yes, so AE dN by Ln into NP naught by e power v by Vt minus 1. This is equation number 9. So combine the equation 1, 8 and 9. We know this equation 1 indicates the total current at x equals 0, which is nothing but hole diffusion current and electron diffusion current. And the equation 8 indicates the hole diffusion current at x equals to 0. And equation 9 indicates electron diffusion current at x equals to 0. Clear? So by combining these two, that means substitute equation 8 and 9 in equation number 1. Now it becomes I equals to total current at x equals 0. Yes, I equals to, what we can write, AE dP by LP plus PN naught, sorry, AE dP by LP into PN naught plus AE dN by Ln into LP naught into e power v by Vt minus 1. So I am taking the term in brackets is constant. I am constant means I am taking one variable, it is I naught. So I equals to I naught into e power v by Vt minus 1. This I naught is called reverse saturation current. So this I naught is replaced with, so I naught is replaced which value, AE dP by LP into PN naught plus AEDN NP naught, AEDN by Ln into NP naught. Clear? So the reverse saturation current is directly proportional to the area of the junction. Yes, and this PN naught is nothing but whole concentration in N region. It is nothing but in N region whole concentration nothing but minority of the charge carriers in the N region. So can we write it is equals to Ni square by Nd? Yes or no? We can write. Why? Because from the law of mass action, minority charge carriers equals to what we can write? Ni square by majority charge carriers. This Pn naught is nothing but whole concentration in N region. Yes, we can write it is equals to, we can replace Pn naught equals to Ni square by Nd. Yes, similarly, NP naught equals to Na square by Na. So this reverse saturation current I naught is directly proportional to the junction area, and this I naught is inversely proportional to the Na and Nd. It's nothing but doping concentrations. Yes, and this I naught is directly proportional to the Na square. Why? Because we are replacing Pn naught equals to Na square by Nd, Np naught equals to Na square by Na. Yes, so I naught is directly proportional to the Na square, and area. This I naught is inversely proportional to the doping concentrations Na and Nd. This reverse saturation current is greater in lightly doped. Why? Because when lightly doped diodes having the more reverse saturation current, and in heavily doped diodes reverse saturation current is very small, and Ni is greater in germanium, so reverse saturation current is more in germanium. Yes, we know in previous discussion only we said intrinsic carrier concentration in germanium is more compared to the silicon. So here intrinsic concentration is directly proportional to the I naught. So when intrinsic concentration is more, reverse saturation current is more. So reverse saturation current is more in germanium compared to silicon. Yes. So this is I equals to I naught e power v by vt minus 1. This is theoretical diode current equation. Yes. But this equation or this diode equation is not fully satisfied by the germanium. It is not fully satisfied by the silicon diode. Yes, this diode equation is fully obeys only germanium diode, but it is not obeyed by the silicon diode, because the practical value of current is slightly deviates from the current obtained using this or above diode equation. To minimize the error between the practical and theoretical values of current, a factor eta is included in the above equation. Now the current equation, or now the diode equation, becomes I equals to I naught into e power v by eta vt minus 1. So here we are using the eta factor. This is factor, so here in typing mistake, or factor eta is included in the above equation. Now this I becomes I naught into e power v by eta vt minus 1. So whatever theoretical value, I equals to I naught into e power v by vt minus 1, but here we are including the eta as extra factor. Because why we are including? Because whatever we derive the diode equation, that is not obeyed by the silicon diode. So there is a deviation of current values between practical and theoretical values. To minimize the error between the practical and theoretical values, we are including the factor or ideality factor eta. Yes. So whatever we derive the theoretical diode equation is fully obeyed by the germanium. So that means eta equals to 1. So eta equals to 1 for the germanium, and it is not obeyed by the silicon diode. So we are considering that eta equals to 2 for silicon. Here also it is FO or for, but here it is FOE. It is a spelling mistake. It's typing mistake. So that ideality factor eta included in the diode equation, that eta value equals to 1 for the germanium, eta value equals to 2 for the silicon. This eta is included in the diode equation to minimize the error between the practical and the theoretical values of current. So after rearranging the above equation, we can write voltage V equals now it written in terms of voltage. So V equals to eta Vt minus eta Vt ln of 1 plus I by I naught. So V equals to voltage across the diode, eta equals to ideality factor, and Vt is nothing but thermal voltage, we know it is nothing but K into T. I equals to current flowing through the diode, and I naught is reverse saturation current. This is the diode equation in forward bias. This is the diode equation in forward bias. What about reverse bias? The same can be applicable for the reverse bias also. Yes, but here the sign is negative. Same equation. So here I mentioned I naught and minus it. Clear? So why this diode equation is not applicable to the silicon? Whatever the we derived the theoretical diode equation is not applicable to the silicon. At small values of forward bias, depletion region width does not become zero in silicon diode. So we are assuming when you are applying the forward bias voltage to the diode, the depletion region width is considered as a zero. But for small values of forward bias voltages, the depletion region width does not become zero in silicon diode. This is the main reason. Due to this, the generation and recombination occurs in depletion region also. Due to this, silicon diode does not obey the equation 10. That means whatever we derived the theoretical value. Hence, factor or ideality factor eta is included. Clear? So why silicon diode is not obeys the diode equation? Because for the smaller values of forward bias, the depletion region width is not zero in the silicon diode. This is the main reason. Due to this, when it is not zero, due to this, generation recombination occurs in the depletion region. So it is not obeying the whatever we derive the theoretical diode equation. To avoid the or to minimize the error between the practical theoretical values, we including the eta, it is equals to 2 for silicon and 1 for zirconium. Clear? I hope you understood this topic. If there is any doubts, you can go through the notes which is already forwarded to you. Thank you.